Dear listener, welcome to my channel. Main topic of this video is image transform. In this video, I am going to discuss fast Hadamard transform with butterfly approach. Now let us start. The Hadamard transform is a digital signal processing techniques used for data compression, feature extraction and signal analysis. It decomposes a signal into set of basis function. These Hadamard functions are square waves with values of +1 and -1 over specific intervals. With WHT transform, the complexity is n into n-1, where n is the size of the signal. I have already published the video on the Hadamard transform and solved the problem for one-dimensional and two-dimensional, and mentioned that what is the complexity, that is number of addition when we are dealing with the signal. But with the fast Hadamard transform, the complexity is reduces to n into log2 n-1. Now in this video, we will see that how we are using the butterfly approach for fast Hadamard transform, and complexity is reduced from n into n-1 to n into log2 n-1. Now this is the Hadamard matrix for the different dimension, that is for 1, 2 by 2, 4 by 4, and this is for 8 by 8. Now we can use either not normalized, but only we require to match the input and output when we are using not normalized and normalized. So this is 8 by 8. So with normal matrix multiplication, the complexity is n into -1. Therefore when n equal to 2, it is 2, for 4 it is 12, for 8 is 56, so it is close to n square. But with butterfly approach, we are getting for n equal to 2 additions, for n equal to 4 8 additions, for n equal to 8 24 additions. So as size of the n increases, we are getting more and more saving. Now we'll see that how to use that butterfly approach. Now exercises on one dimensional signal. X of n is equal to h of 2 into x of n. Now here h of 2 is 1 1 1 minus 1, so this is the signal. Now we divide the signal into half, that is first part is addition and the next part is subtraction, but this is also treated as addition, only the negation operation we are using in the hardware. So first part is x0 plus x1, that is this x0 plus x1 is going, and which will give the capital X of 0, and this x0 minus this x1 we will get the x of 1. So x of 1 is equal to x of 0 minus x of 1. So we are doing the 2 additions. So when n equal to 2, we are doing the 2 additions. Now we'll see that how we apply the butterfly approach to solve the problem. Our signal is 5 and 7. So here 5 plus 7 is 12 and 5 minus 7 is -2. This is the transform signal. To get back our original signal, this is 12 and -2. 12 plus -2 is 10 and 12 minus -2 is 14. And here, as we are using the unnormalized, so we are dividing by 2. That is nothing but the size of the signal. So 10 by 2 is equal to 5 and 14 by 2 is equal to 7 to get back the original signal. Now for n equal to 4, x of n is equal to h of 4 into x of n. To apply the butterfly approach, first we require to see that how the series or how the sequence takes place. So this is x of 0, x of 1, x of 2 and x of 3. So now we will divide this particular portion by the two parts. So x of 0, x of 1, x of 2 and x of 3. Now here for x0, x1 we divide here, and x2, x3. So here instead of this 4 by 4, we will take the 2 by 2, and we will see that all the combination comes when we are adding x0 x1 combination and x2 x3. Now see the next diagram. 1 1 1 minus 1, x0 x1 we are taking only 2, a0 a1, and for b0 b1 we are taking x2 and x3. a0 is x0 plus x1, a1 is x0 minus x1, b0 is x2 plus x3, and b1 is x2 minus x3. Now this is the equation we are getting with the 4 by 4. Now here we can see that this can be arranged with the a and b. So first is a0 plus b0, we will get x0 x1 x2 x3. Now we will add a1 plus b1, so x0 minus x1 plus x2 minus x3, that is a1 plus b1. Now half we take the addition and half we take the negation addition. Now a0 minus b0, x0 plus x1 minus x2 minus x3, we will get this combination, and after that x0 minus x1 minus x2 plus x3, so we are getting this combination. So all this combination of capital X0 to X3 we are doing with the A and B. Now this is a butterfly diagram for the n equal to 4. So x0, x1, x2, x3, we are adding x0 plus x1, we are getting a0, x0 minus x1, we are getting a1, x2 plus x3, we are getting b0, and x2 minus x3, we are getting b1. Now here we are taking a0 with b0, a1 with b1, first their addition and then their subtraction. So a0 plus b0 is x0, a1 plus b1 is x1, a0 minus b0 is x2, and a1 minus b1 is x3. So we are using the butterfly diagram like this way. So here how many additions are there? So here 2 addition plus 2 addition, so 4 additions are there in stage 1 and 4 additions are there in stage 2. So total 8 additions are there. Now we'll see the problem. See the 1, 5, 2, 6, 1 plus 5, 6, 1 minus 5 minus 4, 2 plus 6, 8, 2 minus 6 is minus 4, then here 6 plus 8, then minus 4 minus 4 plus minus 4 minus 8. So this upper part is addition and the lower part is also addition but with the negation. Then 6 minus 8 is minus 2 and minus 4 is 0. So when we take the reverse operation, we require to do like this. Only at last we require to divide by the size of the signal, that is nothing but 4, to get back the original signal. So you try from your side that how this calculation comes at the end. So initially 14 and minus 2 addition, minus 80 addition, then 14 minus 2 subtraction and minus 80 subtraction, we will get this value. Then again we require to do with respect to 12 minus 8, first addition then subtraction, here first addition and then subtraction. Now for n equal to 8, so this is a combination. So if we do the matrix multiplication, we can write like this, but we can reduce with the butterfly approach in a very simplified manner. Now here we will do with the first 4 parts, that is x0, x1, x2, x3 is A, x4, x5, x6 is x7 is B. Again we split this x0 to x3 into C and D, and this 4 to 7 into E and F. See, x0, x1, x2, x3, instead of 8 by 8 we are using now 4 by 4, that is half the approach, and we'll write down all combination. Now we will take the next combination of B with x3, x4, x5, x6 and x7. So this is A0. I hope this is very easy to understand. Now we will take with the B0 and B0 with the 4, 5, 6, 7. So this is the combination. Now with A and B we can represent all the original combination. So first it will take all addition and after that it will take all subtraction. So this is our original. We decompose into A0 and B0. This is A0 we get and B0, and we can see that we can get x0 as A0 plus B0, then A1 plus B1, A2 plus B2, A3 plus B3. So this is the first half part is nothing but addition, and next part is also addition but only negation addition. So A0 minus B0, A1 minus B1, A2 minus B2 and A3 minus B3. Now we again split this, having the 4, we again split into the this into C, this into D, this into E and this into F, because n equal to 8. So therefore there are 3 stages, stage 1, stage 2 and stage 3. In stage 1 with respect to 2, in stage 2 with respect to 4, and in stage 3 with respect to 8. So here this A0 again split into C and D, and this x0, x1 for A and x2, x3, this x0, x1 for C and this x2, x3 for D. The same operation that we applied when n equal to 4. And again we can write down that A0 with combination with respect to C0, D0, C1, D1, then negation addition, that is C0 minus D0 and C1 minus D1. Similarly we can go for B. So for this we can use E, and for this we can use F. We can write down this combination, and this combination, that is all the combination of B, can be represented with respect to E and F. So first two addition and second two are the negation addition. So now see the signal. So first stage 1 we are dealing with, this is nothing but our CD, then EF, then here for example see, for C we are using 0 1 and for D we are using 2 3. So this signal is C, then this D, then this is E, and this is F. So C, D, E and F, and after that this CD becomes A and this EF becomes B, and after that 8 combination. So there are total 8 additions are there at stage 1, 2 addition, 2 addition, 2 addition and 2. So 8 additions here, 4 plus 4, 8 additions on stage 2, and on stage 3 8 additions are there. So in this way we are drawing. So here we are taking the corresponding addition, then with respect to these two, and here we are taking first and the fifth value, second and sixth value. In this way we are doing the addition. So when we solve the problem you will get to know the clear idea, but we require to just do the same things for 2 by 2, 4 by 4 and 8 by 8. So first part is addition and second part is also addition, but with negation addition is there. Now we'll see the problem. 1 2 4 7 3 2 1 2. So 1 2 4 7 3 2 1 2. So we will do with 1 plus 2 3, 1 minus 2 minus 1, 4 plus 7 11, 4 minus 7 minus 3, 3 plus 2 5, 3 minus 2 is 1, 1 plus 2 is 3, and 1 minus 2 is minus 1. So now here we are taking with respect to 3 11 and minus 1 minus 3. So 3 plus 11 is 14 and minus 1 plus minus 3 is minus 4. Then we take respect to their subtraction, that is 3 minus 11 and minus 1 minus 3. Then here we take 5 plus 3 8, 1 minus 1 0, then 5 minus 3 is 2 and 1 minus minus 1 is 2. So in this way, now here we are taking this with respect to this with respect to this, and this with respect to this. So first addition and then subtraction. So 12 plus 8 22, minus 4 plus 0 minus 4, minus 8 plus 2 minus 6, and 2 plus 2 is 4. And in the next half we are taking the subtraction. So in this way it is very easy to solve the using first Hadamard transform, and when the question comes as first Hadamard transform, so no need to write down this derivation in detail. Only important is to draw the butterfly diagram and at every stage show the answers. Now we will do the reverse operation, that is reverse transform. Now here n is 8, so we require to divide the final output by 8. So we are taking on the reverse side, first we require to do this way, then this way, and then the 2 by 2 way. So this is the way. So here this is the half part, so we are dealing with 22 6, then minus 6 10. So first 4 there are addition and second 4 are the negation addition. Then we will do this with this first 2 addition, then subtraction, then 6 4 0 4. After that the stage 3 is again 2 by 2, and whatever the answer we are getting we require to divide by 8 because size of the signal is 8. So in this way we are solving the problem. Now next let us see the another example. So in the forward we are going with 2, then 4 and 8, and in the reverse we are getting this and this. So this is nothing but our CD and this is EF. So 1 plus 3 is 4, 1 minus 3 is minus 2, 7 5 plus 12. In this way we can easily solve the problem. So this is the forward transform. And we can and in the similar way you just try with the reverse transform to get back this original signal. So when you are doing the reverse transform, so you require to divide this at half, then you deal with the 32 minus 8 minus 64 in this way. So you try to do the reverse transform to get the original signal back again. So these three problems are there. So first problem is solved completely with forward and backward. This is the second problem solved with only forward. You try on your side to get this signal back with reverse, and this is the third problem. With this also you try to get the signal back in a reverse way. Now this we solve the problem for only one dimensional. Similarly we can apply for the two dimensional, but you have to remember the steps. For two dimensional, take each row of the signal and apply the fast Hadamard transform. Store the result in row wise. Do step 1 for all rows. This is the intermediate signal. Then take each column of the intermediate signal, apply the fast Hadamard transform and store the result again in row wise. So when we are storing the result, we are doing with the row wise, but only for the first time we are doing first the row wise operation, and in the next we are doing the column wise operation. For two dimensional signal, Walsh Hadamard transform to the, that is reverse. This is for forward, this is for forward, and this is for reverse. So reverse also we require to do the same things, only the last step get added, that as it is two dimensional signal, so at last we are taking the answer, that is by normalizing 1 by n square. So only we require to remember this step, otherwise all steps are same for forward and reverse, only we require to remember this step. So see, this is the 2 by 2 signal, so it is not one dimensional, two dimensional. So what we do, we will take first 2 7 and 7 5 and we will apply the operation. See, this is 2 7 9 minus 5, we are getting the result. We are storing the result in a row wise format. So whenever we are getting the result, we always store in a row wise format. Then the next signal is 7 5, we are taking 7 5, 7 plus 5 is 12 and 7 minus 5 is 2, so we are storing. So this is our intermediate signal. But now first we apply the row wise, now we will apply the column wise. So we will take this signal and their result is again stored in row wise, but initially as a input our signal should be in column wise format. And next is minus 5 by 2, next is minus 5 and 2, so 9 and 12 we are taken in a column wise format, and next 5 minus 2. So this is result. So when result comes, we are storing in a row wise format. So this is the result, right? Now this is our final value. Now we are doing the inverse transform. So inverse transform also we are taking the first row wise. So 21 minus 3 and minus 3 minus 7, we are taking the result are stored in a row wise. This is again intermediate signal because we require to apply the column wise. Now next we will take this and this, and their result is divided by n square, that is nothing but 4, to get back the original result. So see the next slide, that is 18 minus 10. Now we are taking column wise, and 24 by 4, 24 and 4. So we are getting this result, but here we require to divide the result by 4 because this is the final step. So we are getting again original signal back. So only two dimensional, remember that when we apply the fast either Hadamard transform or any type of transform, first we require to apply on row, and whatever that resultant, we require to take the column of that resultant or intermediate signal. So similarly you can apply for the 4 by 4 also. So here only this 4 by 4 is there, and butterfly approach of stage 1 and stage 2. So first we require to apply by the row wise. So if 4 by 4 matrix is there, we will take this row, store the result in row, second row take the result, store in a row, and after that this become our intermediate signal. Then we apply the column wise to get back the final signal into the frequency domain. So this is all about the fast Hadamard transform, and with the butterfly approach we can solve the problem very easily and efficient way, because it requires only n into log to n minus 1 operation, that is addition operations. Thank you.